Hello, sir.
Hey, can you hear me?
I can hear you. Did you have a chance to watch each other's talks, by the way?
I actually did because I just ran it on 2x. So
So, Kostya, I'm going to let you throw out the first ball in this game then. Do you have any questions for Daniel about what he was talking about?
well, I think it's amazing that it's now being formalized that like throughput is not as affected with a cord going out, and generally it was an intuition all of the time. I mean, at least to me. And I also want to pay respect because I built a whole database on some of the papers that were published. So, and I think Scylla follows many of the designs. So, like, I mean, if you look at the paper, it's time for a complete rewrite. But I know it's not one of those papers that I think is also well respected. So, if you look at what Scylla does and some other database technologies nowadays do, like shard per core and all that, and the caching and being put aside and so on. So,
so you're getting to be one of your heroes, is what you get to say, right?
Yeah.
All right, Professor.
I'm more a practical person, yeah. So, but
how does it how does it feel to meet one of your true fans here?
you know,
Professor Abadi, to you. What's your thoughts on this kind of respect?
Sorry, I was just distracted there for a second. Someone was coming at my door. I'm in my office right now. Sorry. So, first of all, thank you for your kind words. It's too kind, you know. But what was the question you asked? I missed the question. I'm sorry.
No, well, I think that Kostya was talking about some of his prior work on Tarrant Tool, and then also about some of how he incorporated some of your thoughts and theories into the work that we've been doing on ScyllaDB. So again, he's a fan from a long time back, right? Kostya, is there anything else you wanted to say?
Well, the intuition about throughput, I was also mentioning that having it formalized is a nice thing, but it has always been the case. Like if you do, like there was this cascading abort algorithm a while ago when you would just pipeline transactions heavily, and if there is any kind of a conflict, you would just abort the entire chain. So that was the intuition about making throughput more available, basically, and allowing more transactions into the system. So just an example of reply.
Yeah, it's interesting, but of course, then you can have a throughput dip when one transaction aborts, then the whole chain aborts, right? You have a massive dip.
Yeah, but there are cases when you don't have a lot of conflict, so
right.
any reason
that's the point.
abort
I mean, that's exactly it, right? So so the reason why it's not really a fundamental trade-off is because of the fact that there is no trade-off when there's no conflict, there's no trade-off, right? So either you do it the way you're describing, or use other OCC protocols, or even use locking. It also works, right? You can lock, and it doesn't matter. No one's waiting for those locks up. There's no conflicts, right? So and the overhead of getting a lock is very small, but it's not really going to affect throughput. So I mean, there's lots of protocols that allow for linear throughput scalability if there's no conflict, right? But when there's conflict, that's when issues may come up, and so so you can't say unlike latency, where latency it's always like you're stuck, like like there's no way around it. Like you want consistency, you have to have that talking to each other. There's no way around that, and that requires that takes time. So there is so with latency and availability, same thing with the cap theorem. Like those are really more fundamental. Like no matter what workload you have, no matter what happens, you have this trade-off between either availability inconsistency or with latency inconsistency. Where throughput, it depends on the workload, and it's only for certain workloads where you do see a trade-off. When you do, it's bad, but it's not for all workloads.
So listen, I just want to say both of you guys are working in totally rarefied air, right? And so Professor Abadi, you went straight on into how this works in various databases. But could you back up and just talk about what is the cap theorem and what is PACELC? Because we have thousands of people who have registered for ScyllaDB Summit, many of whom this is their first time hearing about these concepts. So why don't you just back up and talk to people about what PACELC is and why people should, pay attention to that acronym.
Sure. Yeah. No problem. Yeah. So we'll start with CAP, I guess. That's kind of that's the more well-known one, and that's the one that came first, and
Right.
historically as well. So CAP is really it's some say it's a three-way trade-off, some say it's a two-way trade-off, right? So the way it was originally described is it's a three-way trade-off. It's either you get consistency, or you get availability, or you get tolerance to network partitions, and you can choose two of them, but not three.
Right.
So that's kind of that's the ways it's defined. And the intuition is that if you have, say, a copy of your data in America and a copy of your data in Europe, and you want to do a write in one of those two locations, right? You've got two choices, right? Either you do it in America and then you say it's done before it gets to Europe, or you wait for it to get to Europe, and then only after it's gotten there do you say that it's done, right? So in the first case, if you sort of commit, if you finish a transaction before it gets to Europe, then you sort of, you're giving up a little more consistency there, right? Because it's not the value that currently in Europe is not what's actually the most current value. The current value is the write that's happened in America. So you give up a little bit of consistency, but if Europe were to go down, or if America were to go down, you can always respond with something, right? So you may respond if in Europe that then you get the most recent value, but if America goes down now before the new value gets to Europe, then you can at least respond with the old value. If you allow for that, then you're responding with old value.
That's the highly available. Yeah.
Right. So
now, and in fact, if people want to read more, I put a link in the chat here about our CAP theorem FAQ. Why don't you go on to PACELC then? And because I think that's the one that's the less common one and is the more interesting case. Okay?
Sure. So PACELC is sort of an extension of CAP, right? So the PACELC, the PAC of PACELC is CAP, right? So basically, what it's saying is that when there is a network partition, right, then you have to, as CAP says, CAP says you choose 2 out of 3, but if you have partitions, you can't give up P at this. I mean, P is there's a partition, right? So then you have to choose either availability or consistency. That's the PAC of PACELC. But the point is that the key point of PACELC, though, is that that's not the common case, right? Most of the time, you don't have network partitions, and in fact, most systems these days, a network partition is extremely rare, right? So there's all kinds of redundant ways to get a message from point A to point B, and to have a full partition it's an extremely rare event. So the CAP theorem is kind of interesting in theory, but in practice, there's no real reason why you have to give up between C or A. You can have both. You can have C and A, sort of like in most cases, because it's almost never a partition. So so yet we see many systems, they do give up on consistency, and so the question is why, right? It's not availability, because really there's no trade-off there really in practice. So they give up on availability really for the PACELC theorem says just latency, right? So we talked about throughput a little bit in the talk today, but the main reason why you give up on consistency these days is latency. Is that it just takes time to consistency requires coordination. You have to have 2 different locations communicate with each other to be able to stay consistent with each other. So that takes time to do. It takes latency. It adds latency to transactions. So if you want consistency, that's great, but then you have to pay some latency. And if you don't want to pay that cost, then you get good latency, but now you're going to lose out on consistency. So at a high level, that's the PACELC theorem is saying. It's saying P, when there is a partition, you have to give up, but you have to choose between latency, but you have to choose between availability and consistency. When there's no partition, i.e. the common case, you have to choose between latency and consistency.
Great. Okay, thank you. And for more people, again, there's more than we can talk about in these few short minutes. So I put the link into the chat if you want to read our FAQ on the PACELC theorem. Thanks. Kostya, in specific for ScyllaDB, when we talk about consistency, there's now 2 algorithms for it. We have Paxos and Raft. So do you want to talk about the purpose of each of those consensus algorithms, why we have 2, and what purposes each solve for?
Yeah, and I first would like to just second what's been said. Like this is a trade-off between latency and consistency, and well, consistency requires latency basically. And the thing is, my take at the CAP theorem is that it was really oversold back in 2010s, and because we were looking at it as a fundamental requirement, and we're building systems as if we are never going to go back to strong consistency again. And now the train has turned around completely. Like most of the vendors, they are adding back the strong consistency features. So, and for Scylla, I mean, I guess the biggest difference between Pax and Raft for us is whether it's a centralized algorithm or decentralized algorithm. And decentralized algorithms are just generally, at least in my view, are much harder to reason about. And Raft for us was the main reason we chose Raft over anything else was that its configuration changes, which we use as a basis for our topology changes, as being very well specified, very well tested and implemented, and so on. So if you look at PACELC, it's just, I mean, PACELC itself is not a multi-round protocol, so you have to build on top of that. There are like papers on how you build multi-PACELC on top of PACELC, and so on, how you manage configurations on top of that. And if you are a practitioner, you need some very well neat, complete thing to build upon. And I can say that even when we were looking at Raft, we found quite a few issues, quite a few open issues with the spec. So that's the reason they coexist. And
Right.
I guess we also have eventual consistency, so we could take the best of all worlds. So.
Yeah, I think there's some fundamental architectural differences. Like Paxos is leaderless, right? So it kind of fit more naturally in with the leaderless Cassandra / ScyllaDB architecture. But then Raft now introduces a leader-based thing, but we're trying to make that more resilient by having multi-Raft, right? So do you want to talk about that?
Yeah, for data, we are certainly going to run multiple Raft groups, but this means that every partition is going to be its own consensus, and it's so running independently, essentially having its own leaders. So in the end, we are going to have logically, we're going to have many leaders in the cluster. However, if you look at our schema and topology, this still means a single leader. So for schema and topology, we have all of the members of the cluster in the same group. So we do run a single leader, but it also comes as more or less as an advantage, because the topology state machine is itself quite complicated, and running it in a decentralized fashion without a single leader is also would complicate it quite a bit. So because we have this linearizable is for a layman, just means that you can very easily reason about what's going on, one thing after another. And when you build algorithms, it's a huge value. And you build complex transitions of topology. When you stream data from one node to another, you might need to abort this. You might need to coordinate it with some alter table. It's just much easier to reason about.
Yeah, and Daniel, you put in the chat, strongly agree with that statement. This is when we were talking about that kind of that reverse trend of, everybody was using the CAP to explain the AP bone databases, and now people are moving back. There seems to be more of a blending of SQL and NoSQL concepts and these kinds of, hybrid topologies, or what's known as multimodal databases. Do you want to comment upon some of the trends you're seeing in the industry?
Sure. I just want to say that I agree with even more than what he was saying. What Konstantin was saying, it was not just that the trend has started reverse, but the sort of what we saw in the last decade was that he said that people overreact to CAP. I think it's very true. Sort of like they used CAP as sort of an excuse for why they didn't create a consistent system. Like it's just I mean, it wasn't a good excuse. It was sort of, I mean, they had other reasons, and that's fine, but it really wasn't CAP. And it just, but I think there were probably more systems than there should have been that, maybe at the time they wanted to, if they had thought it through, if they didn't really sort of, if they didn't really drink the CAP Kool-Aid so much, they may have designed the system slightly differently. And I think that's a shame. And as Konstantin said, it's starting to reverse now. But as far as what you're saying, Peter, I agree sort of with that as well, that that you do we are seeing sort of a lot of systems now giving you the best of both worlds, sort of, trying to say, look, it depends on the application. Some applications you really need, like you don't want to do an application that you really want to have database that take care of the consistency for you, since it can often do it faster than the application that can deal with it. And also, just as far as bugs go, you see bugs come up all the time in the application layer. If if they try and do these things, if they say, I'm going to work over a system that does not guarantee consistency, and I'll try and do everything. I'll deal with all the bad stuff that can happen. I'll deal with the application layer. It's just hard to get all those corner cases right. And
right.
you can't, I mean, it's possible. Like, it's not like impossible, but it's just so hard. So so in many cases, it's just worth paying the cost to get the consistency guarantee in the system and be working at a rock solid system. On the other hand, sometimes you just need a performance. Like, it's just users cannot tolerate 200 milliseconds, multiple round trips of that. It's just too long. So and sometimes you don't need it. Like if you're looking at tweets or whatever, and you don't see a tweet, it's probably not going to kill anybody. So it makes sense to have both options, and we're seeing Scylla is one example of this, but there are a lot of systems which are providing options for users. I think that's a good thing.
Go ahead, Kostya. You want to jump in?
I wanted to just add to the complexity problem. There was this research studying various like websites. Daniel, you probably remember the name of this research. It was probably even on the list of the people doing that. But that it was studying Ruby on Rails, Python, Go applications, and how they actually use strongly consistent databases and different consistency levels that are in SQL standard. And it discovers that most of the applications, they actually misuse, they have potential issues in their code simply because they use the default settings for transactional databases, and like snapshot isolation, not serializable.
Right.
So complexity has to be taken into account. Building applications is more difficult and building even more diverse than building databases. So you have to push the problem down to the database layer and provide strong consistency on the database layer to make all the other layers just simpler. So it makes a lot of sense.
Yeah, I think you talk about Peter Bayless's PhD thesis at Berkeley. Yeah, I mean,
okay.
very nice comparison. Yeah, and he said it was people just use defaults. So they don't even know. Like, it's even worse than what I was saying was that, like, they know what they're getting at least, and they just try to design around it, and they hit bugs. But what you're saying is it's even worse. They don't even know what they're getting into. They're just using the defaults of the system, and it's not and not getting full isolation, and not getting full consistency. And they don't know until they deploy the system. They see weird stuff happening. Like, wait, what happened? They didn't even bother trying to change the default. I mean, it's a little bit, I mean, that's an extreme case. I mean, that shouldn't be, that shouldn't happen. People should at least know what they're doing. But even if you know what you're doing, still sometimes you still want to have consistency.
Now, I'm going to throw one more question out here for Professor Abadi. It seems to me that it's been difficult for SQL vendors or traditional RDBMS systems to loosen their consistency guarantees, where for a NoSQL system, it seems like, again, like you take a look at ScyllaDB, we've been adding Paxos for lightweight transactions. We now have stronger consistency with Wrap. It seems that when you start with an classic AP mode system, it's easier to add layers to consistency as opposed to loosening them once you already started with that CP mode thinking. Would you agree, or what do you think?
Well, that's a controversial statement. You're not going to agree to that all the way.
Okay.
It's kind of like it depends, right? Because first of all, when you say easier, what do you mean by easier, right? You mean easier like in like what does it take? I mean, but is it easy to add it without losing too much performance? That's much more tricky, and it kind of depends where you started. I would say both directions is often harder than expected, to do a good performance, because either way, you designed to making one set of assumptions, and now you're changing what you want to assume. If you start from the beginning, you to assume that you made different paths, different different design choices. So it's sort of, really the ideal way is to say at the beginning, I want to be able to handle both, and design something from the beginning, say, with both options. And whenever you bolt on something at the end, it can get a little bit, unideal, I guess, as far as performance goes. You may be adding more latency than you need to, or adding more throughput reductions than you need to. It kind of depends. So I wouldn't make a statement, but it's I guess maybe some cases it's a little bit easier.
How about you, Kostya? What do you think?
Peter, DynamoDB is a good example. So DynamoDB started as using vector clocks and being eventually consistent. And if you look at watch the modern talks on DynamoDB, you'll see it already provides transactions and even multi-precision transactions. But what is even more interesting is, well, I don't actually know what they used initially, but they say that they started using B trees for storage. So if you look at it from the point of view of how your design choices are correlated, like log structured merge trees are very convenient for write-only transactions, like only blind writes. And you don't get that many when you start using your database in a strongly consistent manner, because it's not just about consistent log of changes. It's also about reading your own writes. So the scenarios in which you use a strongly consistent transactional database means that you actually read more before you write. And that means that you are better off probably with a different storage engine for the database itself. So it's really connected, and well, probably you can build a system that achieves everything, but it's also complexity.
Fair enough. All right, Professor Abadi, I'm going to give you the last word today. If people want to learn more about this, what would you suggest? Where should people go to find out more about consensus algorithms in the year 2023?
This should enroll at UMD and take my class.
Fair enough.
There's not a good textbook on it. Like, it's really not. It's a shame. In my class we sort of use like readings from here and there and so all over the place, because it's not really in one place. Sort of put together nicely. I don't have a great recommendation. You can read some of my papers, I guess. Go to our website, but it doesn't have it's just a small subset of what's out there. So I mean, not a good option except for just to take a class. I guess. I'm not sure.
Fair enough. Well, if anybody in the audience would like to sign up, University of Maryland is accepting applications. Professor Abadi, Kostya, thank you so very much. We're going to go on break now. But again, look forward to work of both of you over the next coming months and years. And thank you so much for being here.
Thank you. See you.